Ready? Okay. All right. So I'll get started. Okay. Well, we left off our intrepid rod last time after calculating what it looks like to bend it and twist it in the small bits. So we started out looking at taking a small cross-section and asking what torsion looks like. And what I mean by looks like is I mean what's the elastic energy cost for performing a certain defined deformation to it, in this case twisting it. And we also looked at the case of bending. Of course, what I'd like to do, and I think you'd like to do too, is not talk about little pieces of the rod in isolation and not just do mechanics, but we'd like to look at, say, a thermal ensemble of wiggly rods. To do that, we need to describe a rod not just locally in terms of little pieces getting bent and twisted, but talking about how do I define some more arbitrary configuration of a bent and twisted filament. So if you think about it, there is at least it can't be that hard to figure this out, because at each point, we know that we have a local tangent vector. If I had to reproduce this curve for you, what I could do is I could tell you the following thing. I could give you a little magic ball, and in that magic ball, I'd have a vector, which is a unit vector. So it would sweep out on the sphere. And it says walk at 1 meter per second. And this thing will keep wiggling around and just keep going in the direction that this little thing is wiggling. And that's going to define this space curve. So the dynamics of this tangent vector wiggling around on the unit sphere better, in fact, reproduce for me any configuration of a line. And of course, that's going to be true, except I'm going to miss my torsion term. I'm going to also have to allow for the possibility of the rod itself rotating about its own tangent vector if I want to include both pieces. To do that, I can embed in one of my little bits of rod a local body fixed coordinate system. And following Landau's notation, the body fixed coordinate system is in Greek letters. So I have eta and xc in the plane perpendicular to the length of the rod. So in the undeformed state, zeta, which is along the axis of the rod, would just keep going straight, and you would have this parallel to, say, the z coordinate in the space fixed frame. So could have something like this. So what I really need to keep track of is not just my tangent vector, but I need to keep track of the rotation of this piece about its tangent vector. And if I have both pieces, I have a complete description of the mechanical state of deformation of the rod. Now, fortunately, you know this can't be any more complicated than a series of rotations of this unit vector, either about its own axis or about some other axis. So I can define a rotational velocity in the following sense, that if I move an infinitesimal arc length piece, dl, along my filament, I have an infinitesimal rotation, which I can write in terms of a vector that tells me how each little element is infinitesimally rotated relative to the previous one. I call it a velocity, but I shouldn't. I think I really should call it I don't know what I call this, because this is a distance, not a time, but you get the idea. If you imagine traversing the curve at a fixed velocity, the two are different only by a number, so I guess I don't care so much. So, given this notation, then what we talked about last time becomes fairly straightforward in the sense that the piece of this vector that's parallel to the body fixed axis along the axis is just torsion. And the part that's perpendicular to this axis has to be bending. The only new feature we're adding is we're allowing this to itself change with L in some complicated way, so you can spiral around and make the shape of Mickey Mouse if you choose to. So if I have to write down the rate of change of the tangent vector with arc length along the curve, what I'm saying is that has to be the rotational, quote, velocity crossed into the tangent vector itself. So this, of course, guarantees that t doesn't grow in length and it stays a unit vector. All it does is it swings around, and if I have my little object here, I see this thing wiggling around on the unit sphere, and if I were to have a fancy vector with, say, one side painted red and the other side painted blue, I could see it twisting about itself. So that's about all that can happen. What I'd like to do, though, is I'd actually like to write this rotational velocity vector. I'd like to decompose it in terms of the torsion and the bending pieces. The easy way to do this is to take the cross product, which gives you a triple cross product. And this is, you can write this out in terms of, well, I learned this as the back cab rule. You might have learned it as the Lagrange identity I learned recently, but I guess in public school it's the back cab rule. So there it is. And now it's pretty clear that we can clean this up a little bit. We can solve for omega here. Let me slide this up and get a final result, which is the decomposition of my angular velocity in terms of a piece that is purely along the local tangent and a piece that is purely perpendicular to the local tangent. So this right here is bending, and this right here, well, is torsion, but a torsion has an R in it. So there you go. That one, here we go. Oh. I was thinking it was Tom Lebensky's blood dripping down here, but it's actually just water. That whole thing yesterday startled me, I have to tell you. Okay. So, a little bit of notation. It's useful to think of the piece, to think about, we talked yesterday about a radius of curvature. We can connect that to the current version of the problem by saying that at one point, if I have a tangent vector going like this, I can think of the circle that just touches at this point here. And this, in fact, has, if I think of a local normal to the surface, the curve like this, then the radius of this circle, r, is exactly what I meant by the radius of curvature before. In other words, if I take the part, if I write dt dl, this is 1 over r times the normal. So the magnitude of the rate of change of the tangent vector at this point is the inverse of this radius, which was my curvature before. So that connects all the pieces back together. At this point, we should be able to write down an elastic energy for any configuration of the rod you want, currently specified by a series of a vector here, which is a omega of L. So you give me an omega of L, I should be able to tell you 27 ergs, or whatever number you like. Yeah? T is the tangent to the curve. Yeah, so I have a body, so I have two coordinate systems in the world. And what I'm saying is that the Greek coordinate system is rotating about the Latin coordinate system. So the Greek coordinate system, so like think this is very similar to thinking about the precession and spinning of a top, if you like. So you have a body fixed coordinate system in your top, or in this case, in your chunk of rod, and that's the Greek one. And it spins in the space fixed coordinate system, and the omega is telling me what's the connection between the two. No. T is always going to be parallel to the zeta axis. Yeah. Yes, that's right. I want to, in the end, have just T, though. Okay. In fact, well, let me come to that in a second, maybe. So let's write down the elastic energy. So what kind of terms can I have? First of all, I have to have some sort of quadratic form so that the minimum is going to be the straight rod configuration. I can't have terms of the following form. I can't have a coupling between twist and bend this way, because in my definition of this body fixed coordinate system, I could have selected my zeta axis to go the opposite direction. So I can't have terms that are odd in numbers of zetas, because I can't have a term that changes sign in the energy if I decide my zeta pointed the other way. So for that reason, I have to have my torsion term, which we actually calculated last time. That's a horrible zeta. The reason I like T is I can write it. There we go. So this is going to be my torsional energy density. It's in the shadows, in fact. Let me move that down. Plane. I have a general bilinear form. I have no extra rules not allowing me to mix these. So I know that these involve the Young's modulus, which we calculated from bending. And here I have, as we calculated last time, my moment of inertia tensors. And I'm allowed to have a mixed term. Of course, you can write this bending energy This is a general bilinear, symmetric bilinear form. And of course, we can diagonalize in this subspace in order to get the principal bending directions, in which case we can always write this as two independent pieces like so, by diagonalization. The net effect is that at the end of the day, we have an elastic free energy for the rod that's, of course, an integral down the arc length from one end to the other of these energy densities. And if I work in the frame where I have diagonalized. I have a complete description of the elastic energy in terms of anything you want to do to my filament. And I'll get back to T in a minute here, Leo. In terms of the vector that's telling me how this is how omega, this angular velocity, is itself moving around as a function of arc length. So in principle, these omegas are functions of s, and I have to do an integral. From this, you can calculate what the bending moments are that are required to hold the configuration like this. And it's a simple exercise to take the derivatives to get, in the way I've written it, this is E1, and we'll use this in a minute. So I'll put this up for future reference. E2 Gesundheit, and here's the torsion. So now we have all the bending and twisting moments written out. Okay, so.
These moments would be the analog of angular momenta?
Yeah, well, that's right, yeah, so exactly, because if I forget about E, in fact, this is a moment of inertia times a angular velocity, and I would think of this as the angular momentum if I thought of arc length as time. So if I go back to my little ball, that would be the top spinning around in the picture. Okay, thank you. So let's put this, we're going to use this result here mostly. I would like to now be able to say, do a slightly different calculation. I'd like to say I want to apply either body forces to this rod. I could imagine a hanging chain. I could imagine taking a rod and pulling on one side or pulling up in the middle. I could imagine applying torques to the rod in various places. I could take a stick and twist the two ends and ask what shape do I get. So what I'm going to do first is I'm going to calculate what is the ground state of this rod if I impose boundary conditions that aren't compatible with it being straight. So how does it find a minimum energy solution? These are the equations of equilibrium. Essentially what we're going to be doing is solving f equals 0 over and over again here. So I think the easiest way to do this, actually, is to go back and consider a slice of my rod here, where this is my zeta axis here. And I'm drawing it as if it has a circular cross-section, but again, you know, we aren't obligated to do that. It's just I can't draw. Now, you could imagine in this little piece here of length ds, I have a force being applied to the top surface, like so. I'm going to write this as the force plus a little bit extra. Why? Because there's also a force down here minus F pulling on the other side. So imagine you have your rope or your stiff, piece of bamboo, and you're pulling on it in various ways. Well, you know in mechanical equilibrium, the net force on this has to be 0. In fact, you could imagine that there's some sort of potential that is also putting a body force on it. So I can add a body force, which itself better be proportional to the length. If I go from ds to 2ds, I better get twice the body force here. And now all I have to do is write down force balance. And it's fairly easy to see, just taking this plus this plus this equals 0, that you end up with something fairly easy, which is just saying that unless you have a body force, the rate of change of the total force in the filament is 0, which is simply saying a filament does a good job of transmitting force from one side to another. Now, the thing which is whoops, I get extra boards here. Good. Exactly. So, yeah. In fact, if you look at Galileo's well, I've never seen it myself, but I've seen reproductions of Galileo's treatise on mechanics, and he has a picture of a beam sticking out of a wall, and he said, well, the beam sticking out of the wall has to deform, flex downward a bit. How do I understand that? So that's your case of gravity acting on the beam. You could imagine more exotic versions, but that's the one that comes to mind for me. So, let's see. Okay. We not only have to balance forces, though, but we also have to balance torques. So let's think about that a little bit. Here again, I'm going to compute my torques about the center of the top surface here. So I have a torque, or a moment, applied to it, which comes from whatever is above this piece acting on it. I have a torque acting on the bottom piece. So far, this looks precisely like what we had before, except not quite, because if you recall, I also have this force minus F, which if I'm computing torques about the top, actually has a moment. Now, the force on the top, I chose this one to eliminate the moment of that force. But here, I have a vector which is minus ds, like so. So if we do torque balance, we end up with m plus dm. I'll write one, since I didn't write the other one out, I'll write this one out. But it's slightly more interesting. This looks ungainly, but I just wanted to help you keep track of minus signs. Turns out two of them cancel out. That has to equal 0. So the collecting terms, you end up with a, and of course what I mean by this is the magnitude of ds in the minus zeta direction. If you work this out, you end up with this as another condition. So the new feature here is that the forces that are on the rod can in fact exert bending moments on the rod if they're not collinear with the local direction of that piece of rod. So it's not terribly surprising. We now have differential equations, not maybe in the form we want yet, but the differential equations that allow us to solve for the shape of the rod under certain conditions. I'm going to look at one or two solutions just for fun, and I'm going to take the body force to be 0, so we're going to turn off gravity, just to make a nice problem. When you do that, though, you have to decide what kinds of boundary conditions do you want. There's a whole engineering nomenclature for these. You can imagine, like, the case of a beam coming out of the wall. The position of the filament and its tangent are constrained at this point. These are called clamped. You can also imagine putting a hinge here, so the position is constrained but the angle is free. And you can also imagine a free boundary condition, where here you don't have any condition on either the local slope or the position, but you do have to have 0 force and 0 bending moment at the end. And I don't want to go through all of the ones that, there's all kinds of mixing and matching of various boundary conditions you can think of, and you can think about that yourself. And it's also in the notes. To set up our problem, let me specialize to a circular cross-section. And so I'm going to say circular cross-section. I'm going to say I1 is equal to I2. The advantage of doing so is it makes the bending moment in this C eta plane collinear with that piece of the angular velocity vector. And now what I'd like to do is I'd like to write out the equation for the total bending moment in terms of the tangent vectors. So First, let me recall that the torsion piece is this, and we see from the middle top board that I can write the twist in terms of my torsion modulus and my twisting moment to set things up. I can now calculate the rate of change of the twist piece. And of course, this has two parts. I'm simply taking the derivative of the first piece. However, I know something nice about that. This has to vanish because whatever direction this is pointing in, it's perpendicular to t. So the dot product with t goes away. So that's nice. The second term looks like this. And then using, in fact, my earlier condition, I will skip one or two algebraic steps because I think it's both not illuminating and it gets boring quickly. We can arrive at the following statement. So now, if I use from my energy calculation, I can see that using m's, I see that, in fact, and for a circular cross-section where this is the case, m perp is, in fact, collinear with omega perp. The advantage of that is that I can now see that I've actually calculated both the piece along t and the piece perpendicular to t. So the piece perpendicular to t, this is just a slightly complicated way of writing the piece of omega perp, and this is simply a simple way of writing the piece, the torsional piece. So let's see. So collecting, that's the only one, okay. Collecting my pieces, I have the torques purely in terms of the t's, which is where I wanted to end up. So what you can see here is I simply now have the local bending moments in terms of the amount of bend, or the local moments in terms of the local bend and the local twist. So from this, it's from this result, well, finally, I should have that on the board somewhere. Right. So I'm going to do collect pieces. I end up finding that, in fact, both of these will drop out because, well, this is orthogonal to dt ds, and this is 0 because this is the total derivative of t squared, which is 1. So what we've done is we've eliminated bending and twisting, coupling between bending and torsion. No bending, twisting, coupling. this up a little bit. I'll pull it down in just a second. So I'm going to ignore from now on the torsional piece. And if I do that, so I'll say no torsion. I actually have a complete set of equations because I have not only m, but I also have dm ds over here. And from that, so what I'm going to do is I'm going to take an s derivative of this term, and then I'm going to say that's equal to f cross t. Okay? So here's the thing. If I take an s derivative of this by the chain rule, I hit this one first, but that gives me the same vector crossed into itself, so it vanishes. The only term I need then is t cross the second derivative here. Yeah, sorry. I'm sorry, I didn't understand.
Are ds and dl the same?
Oh, yes, they are. In my notes, I have all L's, and on the board, I thought I had all S's. Did I? Oh, I'm sorry. There is no L. In the shadow over here? Oh, I do. You're right. Sorry. Okay. Well, thank you. I will endeavor to make more interesting mistakes next time. So, okay, now we're actually in good shape. So taking this equation and our friend here, we have the following. S, there we go, is S, F cross T. As a final step, we've set up our equation of equilibrium. I want to write T as dr ds so I can make contact with the position of the filament as a function of arc length. Okay. So let's actually take this equation out for a spin and see what it does. Here's an example problem that actually I found interesting. I think I will, let's see how we're doing on time. Since I think I'm doing okay on time, let me take a short diversion here. Does that look sort of erased? Okay, let's. Yeah, it's kind of is. That's why I was wondering if it was going to do okay. They're all kind of damp. Yeah. There's one here? No. Let's see if this. No, that's making it worse. Okay. Okay. Well, I think that's the best I can do.
Christine Backlund is hiding 2 layers back.
2 layers back. Oh, I forgot about your system. There's a third. Yes. Okay. Okay. Well, I think I'll need to recruit a team of people to hold me up. So, a short digression. I want to tell you about an experiment that a colleague of mine at UCLA, Giovanni Zocchi, worked out. So, there is a protein called guanosine kinase, which looks a little bit like a kidney bean. And it is a protein that eats an ATP, burns one up, essentially 1 unit of fuel, and phosphorylates something else. So it's part of the phosphorylation, dephosphorylation economy of the cell, which I don't understand. But it's kind of clever because only when it's attached to its substrate, the thing that it's going to phosphorylate, does it eat ATP. It's a little bit like your car. You get to turn it off when you don't want to go somewhere. You don't have to leave the motor running, burning fuel when you don't need it. The question is, how can it be quite so clever? And apparently the way it's clever is that when it binds to the substrate, the thing that it's going to phosphorylate, it deforms a little bit. And when it deforms a little bit, only then can an ATP bind to it. So this is an example of what's called allostery. Giovanni said, I would like to understand the mechanics of allostery. And there are lots of people who do single molecule experiments by pulling on proteins really hard. And typically what happens is they unravel like a sweater. So that's kind of not what he wants to do. This is a little bit more like if you have a watch, you might want to see how it works by smashing it with a hammer and pulling out the parts. Or you could say, let me twiddle the knobs first and see what I can do sort of gently. His idea was the following. Glue a little sticker to each side. This sticker has a piece of single-stranded DNA. So, like so. Put this thing in a solution. So let's call this strand A. Let's call this strand B. Put this in solution with a bunch of single-stranded DNA that has the complement of A on one side and the complement of B on the other side. What you end up doing is you end up producing your kidney bean here and a stiff, now double-stranded piece of DNA like so. This is essentially the same mechanical problem as an archery bow. So the DNA is like the piece you hold, and then this is the bowstring. So what you're doing is you're putting this protein under tension. Now, if you're very clever at biochemistry, you can glue these points to different spots on here, and by changing the length of the DNA, you can calculate the force that you're applying to this. You're not quite done yet, though, because, of course, chemistry isn't quite so clever as to just make this. In fact, that's fortunate. It's a sulfur. This is a cyst. What you have to do is mutate this to have a cysteine here. Yeah, and then you have this type of sulfur chemistry with a thiol to it. It's like the thiol gold binding thing. So there's a number of very clever biochemical steps, and if you want to actually see, as he did, the change in biochemical activity of the protein as a function of pulling, you need to convince yourself that you can glue all this paraphernalia onto it and have it still work and all these things. So there's a number of steps I'm not talking about here.
Also, can you control the way the swivel around the thiol linkage?
Yeah, this is, as far as we know, a flexible bit, and it's free to spin around here.
So it might go around.
Yeah, it might. We don't know that, in fact. But presumably, as long as, well, I certainly agree with you that you could take this bow and spin it around this way to see if it helps you. Yeah, and that I can't control in this. You had a question, I'm sorry.
Could you explain again what the bow is?
The bow is double-stranded DNA. Maybe I should draw it the following way. So what's happened is that you now get the base pairing interaction to work for you. And the way that works is you now have A and A complement forming a double-stranded piece here, and you have B and B complement forming a double-stranded piece here. So the trick that makes this go is that the flexibility of single-stranded DNA and double-stranded DNA differ by about a factor of 50. So this is very flexible right now, but as soon as you do this, you've made a stiff object. It's kind of like saying you constructed the archery bow on top of the bowstring. That's, I guess, the right way to say it. This is a short, flexible linker. Well, this is under tension. So this is being pulled because the DNA wants to be short. This is much shorter than we'll talk about in a few minutes, the persistence length of the DNA. So the DNA is doing its best to straighten itself out, but it's being prevented because the two ends have been tied together by this protein. So the protein is under tension, the DNA has been bent. So.
Some other ingenious way of providing compression?
Not that I know of, but that would be, of course, fun. The only thing you can do is you can pull from different sides at this point, and you can pull with different strengths by changing the length of the DNA. Yes? Oh, what you do is you actually have to put in solution, and this is again beyond my skill set here, but you have to take the single-stranded DNA with a special linker that binds to the cysteine here. So this basically, you have the parts of the experiment are protein pieces like this and magic spots that you have actually mutated the protein to put them on there. So then this thing self-assembles. The trick, though, is that you actually end up with a chemical equilibrium of monomers and dimers. Now, of course, depending on the concentration, well, that's a bad one, but you get the idea. But in fact, that's vital. The reason it's vital is that notice these two configurations have exactly the same base pairing energy. Everything is the same except for the fact you're not doing elastic work. So now what you can do is you can use standard biochemical techniques, which in this case involve running these things through a gel in an electric field, and you get different mobilities depending on whether you have dimers versus monomers. But in fact, what you see is you see two bands, one associated with the monomers that run farther and the dimers that run less far, I think. In principle, but if you don't have too high a concentration, you can, if you find the right sweet spot, you actually don't see enough of a trimer band to matter. But in principle, you can analyze it with N-mers if you needed to. So, but that's actually true. So the idea is that the difference in concentration between the dimers and the monomers is in fact exponentially sensitive to the elastic energy in the system. Because there's in fact the only thing that shifts the chemical equilibrium between this structure and this structure, other than boring factors associated with the concentration of the proteins, is the fact now you've created this structure with energy put into elasticity versus one where you didn't. Yes? Yeah. You get a lot of energy from the base pairing interaction. So essentially what you're doing is you are doing work on this protein, and the fuel, if you like, is the binding energy of these hydrogen bonds between the A's and the T's and the C's and the G's. So this thing zippers itself up. So in fact, let's see. Let me, now I can't slide that one up.
But you could slide the middle one up.
Slide the middle. This one? Here. Wow, look at that. Okay. So, based on this calculation, what you really want to do is you need to be able to work out what is the force that you're applying for a particular curvature. I'm not going to go through the whole calculation, but I wanted to use this as kind of a cool example to motivate the idea of solving the elasticity of rods in effectively a t equals 0 environment.
But then to close the loop, you went and measured the change in the ATP hydrolysis rate as well under tension?
Actually, he measured the production of phosphorylated other guys under tension. Yeah. Yeah, so you have another chemical signal. You put in the unphosphorylated substrate, and then chemically you can watch the growth of the phosphorylated version of it.
Presumably the new concentration of broken those strings as well.
Yeah, floating around, which you hope doesn't matter. In fact, there's no way to know how much that matters, except for the fact that when you put a very long piece of DNA on here so it doesn't really want to bend much, it's easy to bend it, then you get pretty much back to the reaction rates that you had when you just had a glass of this stuff in the substrate. So you think you're doing okay. And in fact, what you can see is that if you pull in certain directions, you can suppress this reaction. If you pull in other directions, it doesn't matter.
The directions are controlled by what you use.
Yeah, exactly. So that's the trick, is you can't sort of arbitrarily move around. You have to do 3 examples and call it quits. So, because it's a lot of work at that point. So anyway, I just wanted to bring this up as I think it's a cool experiment, and it motivated me to solve the following problem, which we'll do right now. Let's consider a rod. So let me consider half of the DNA, because presumably the structure is symmetric about the midplane. So I'm going to start the thing off.
How many proteins are symmetric about the midline?
Oh, I don't care about the protein. I claim about the DNA. Yeah. No, if you want, I can put, here's you on the side if you want, and it's just as good as far as I'm concerned. So I can imagine here's my piece of bowstring, or I'm sorry, bow, the wood part. So I can write down the following. I have a position of this thing, which looks like so. And now I can start computing derivatives and calculating this problem here. So for instance, this is the y direction, this is the x direction. I'm going to need the magnitude. I'm not going to work it out on the board because it's just long and it's all in the notes. I'm going to need the magnitude of this term. It is, but the problem, well, the feature is that I found that out to my sadness only after I cranked it out. That's true. I mean, he didn't live long enough to solve Giovanni's problem for him. So I'm sure Giovanni would have said, if I could have talked to Lando, Alex, I really wouldn't have needed you. But, So the other side, of course, is I have F cross T, which is drds. So I'm just going to build this equation for you. And what I end up getting is something that's going to look very familiar. Here's the left-hand side of the equation. The right-hand side of the equation ends up being F. And I think I have to get the signs right. Yep. F sine theta. And you can try this yourself. So you'll notice that the net effect is that you have an equation that looks very familiar. For this angle, where, I'm sorry, I should have, there we go. Superscript. This third derivative. Yeah. Oh, yeah, that's a bad 3 is what you're telling me. Penmanship is not my strong suit either, it seems, but there we go. Okay, so now you've probably seen this equation before. And can anyone tell me where? Pendulum. Thank you. Where, in fact, the one parameter that enters here is the force over this bending modulus. And if you check, this has dimensions of inverse length squared, which is just what I need for this to be dimensionally correct. So you might say, well, this looks like a mess. But there's a first integral, of course. You can see that if I multiply through by theta prime, I can write this whole thing as a total derivative of something that looks like a kinetic energy and something that looks like a potential. Like so. You might want to worry that I'm multiplying through by 0. So what happened to the straight solution? I'll come back to that. So just keep that in your back pocket for a minute. So what I'm saying is that assuming that's not the case, I know, in fact, that I have a first-order differential equation, so I can just write this as an integral. I do need my boundary conditions, though. We talked about that very briefly. Oh, wait, you see that? I do learn from experience. If it worked twice, it'll work the third time. So there we go. So boundary conditions. Well, what do I know, actually? I know that I start going straight up. I don't know, but what do I know about over here? Well, I don't know what angle I end up at is the thing. I don't know whether my archery bow is bent like this or just barely bent. So I know that at 0, Well, I do know the following thing. At the end, at s equals L, let me say, I have a torque-free boundary condition. Notice the rate of change of the angle is, of course, the second derivative of where I'm going, and that's telling me about the bending moment on the end. So I'm claiming that there's no twisting moment on the end. And I'm also going to say that there's the final angle I'll call theta naught. So that actually sets my constant here. It means that c is minus f cosine theta naught. So this is sufficient to let me write cosine theta minus f cosine theta naught. You might argue, well, you don't know what the final angle is, and you're right. Let me come back to that, though. So now I can simply turn this into an integral so that the local, there's L again, the local arc length is an integral over the angle, so I'll use that as a dummy variable, cosine theta bar minus cosine theta naught, which is my as yet unknown boundary. And I have this factor of square root of 2 little f out front. So there we have an answer. And we need, sorry? Yeah, I'm sorry, I didn't see that. I was, hang on, picking up my notes. Yes? Oh, because the rate of change of the angle is related to the torque or the bending moment that I'm applying to the end. So in principle, I could imagine, here we go. I could imagine I put a force on the end of this thing. In fact, I did. My protein plus linker did so. But I could also imagine taking the end and twisting. I claim there's no twist on the end because there's a hinge, effectively, that's, you can think of this as, imagine I tied through this hole a little string and I pulled down hard. So the problem is I jam this into the table, I tie a string through here that can't apply any torques, but I can pull down as hard as I choose, or, you know, and then this thing bends a little bit. Okay? So that's, right, yeah. So a different condition could be I could grab the end and apply a fixed torque. Yeah, exactly. Or I could set the angle at the very end, or the rate of change of the angle. I could pick either way. And there's a whole list of funny names for these boundary conditions, like freely supported and clamped and hinged and so on, which correspond to those different problems. So as a final point, we get theta naught from the condition that if I do this integral, s out to the end, let me make sure get that. So if I integrate all the way to theta naught, I better get the total length of the filament back again. So I have to use all my arc length to get there. And if you want to actually get the shape, now of course this integral is a bit of a mess, but you can, in principle, think about it. Just to finish the job, let me point out that based on our definitions, you can recover the entire shape of this thing, like so. So in fact, this solves the problem. Of course, this is an integral that I can't do in closed form, but that's okay. I can at least compute this as I need to. I want to compute something that I can do in closed form, just to finish this up. So let me look at a particular limit that at first seems somewhat uninteresting, but I think it actually teaches you a nice little trick at the end. So finally, look at small bending limit. Just for kicks, let's turn this into an integral we can. Yes? No, please. Yes? Yeah. You know, the theta, the angle can have it doesn't have to be 0 or pi over 2 or anything, but yeah, but it has to be going straight at the end. It can't be curving. Yeah, even with the f. If I twist it with a torque, I can have a yeah, that's right. Because remember, the angle essentially is the first derivative of dr ds, really. So that's why. Does that make sense? Okay, good. So let's do something you can do. Let's do, if we take small angles, then in fact I get to do the following thing. I can say that, well, theta not small, theta bar is always small too. It's near 0. So I can expand the cosines to quadratic order. The linear terms go away. The 2 kills the square root of 2 that's floating around. And if I now say I integrate to the very end of my filament, I have the following equation, which is kind of funny looking. And I'll tell you why I think it's funny in just a second. I should let you decide how funny it is, really. So z will be my integration variable. And since I expanded, I have quadratic pieces, and the 1's canceled, and the 1/2's killed off at 2 that was floating around over there. If I now rescale things, I can actually pull out all of the theta not dependence, which is the weird part to me. And you're left with an integral that even I can do. There you go. Turns out you get pi over 2 times, of course, the stuff in front. You should find this a little bit disturbing, though, because in principle, I should get to apply any force I feel like, right? So what went wrong here? Well, think about it this way. L should be a fixed number, but if I really believe this equation, what it's telling me is that L versus F is coming down like so. Now, there's actually some real length of the filament here. If the force is sufficiently big, of course, what it's telling me is the small angle approximation has failed. And in fact, I'm not getting enough length because I need to bend more. The top has been being pulled down. I need to curve a lot more to get all of my arc length in to get to the end. So that part isn't so bad. But what happened on this side? All of a sudden, I get too much length. So how can I fix that? The only way I can fix that is say that there can't be a solution. I'm sorry. Yeah, I thought I heard something. Yes. Yeah. Oh, so I'm not worrying about going over the top. So the equivalent of that would be doing a loop-de-loop in my curve. So yeah, in principle, you could imagine, I can't do it with this, obviously, but I could take this and crank the heck out of it. And eventually, there would be some solution that does a loop-de-loop. And that would be going over the top on the pendulum. I'm not doing that, though. In fact, I'm at the very far other limit where the pendulum is basically just hanging there. And I'm barely wiggling it. So here's the funny thing. Notice that if F is less than, basically if I just solve for F in this equation, I find the following result. I can't find a meaningful solution for the bent filament this way if F is too small. This actually is the limit for the Euler buckling instability. So it's kind of a funny way to derive it, but what it's saying is that if you're pushing down on this filament with a force smaller than that F given there, you can't find a bent solution at all. And the reason that the math went a little bit haywire here is that there's actually a hidden solution built into this, which was theta prime equals 0 the whole way up, and I've neglected that by multiplying through by something that had to be non-zero. So in fact, this is the Euler buckling limit. Okay.
Small oscillations associated with potential.
These small oscillations are, yeah, exactly. Well, that's really what I've done here, right? So I guess what I have then, I have 1/4 of a period of a small oscillation in my solution. So I start off at the middle, if you like, and I go and get to the end. And then the rest of the small oscillation, I guess, would correspond to the other root, which notice that I had a square here, so I had 2 roots. I could have gone the other way too.
The boundary conditions prevent you from going back and forth.
Yeah, I'm not. Yeah, exactly. Yeah. So I've only since arc length is time. What I've done is I've integrated out to the point where I'm done at the end. Yeah. Yeah, it's a good question. I didn't think about that. So. Yes, it's exactly the same. There are, if you're very careful, you have to watch out for which Euler buckling problem you're doing. It turns out that you could imagine forcing the rod to be straight on the top and the bottom, in which case you buckle like this. And that's a slightly higher one. This actually is exactly the answer for doing the following one, where you've clamped this end down like so, and you push down, you get a curve that goes like that when you buckle. And that's exactly, in fact, the boundary conditions we set up, because by symmetry, I set this thing up to go straight up at the beginning. So it's the right one, even down to the pi squareds and the 4s and so on. All right, so that's enough of t equals 0 mechanics. If we have the equation for, if we have the energy of a filament, I should be able to ask about a statistical ensemble now of wiggling filaments. The difference is here I was inspired by a very small piece of DNA, much smaller than the typical distance over which you see it wiggle. What I'd like to do is try to convince you that we know what that distance is. So, I think actually it's what I'd like to do is take a 5-minute break. Sorry, I think I kept you too long. Oh. Let's see. I just gotta. Oh, okay. I was just trying to dry it off. Oh, you can? Okay, fair enough. Oops, sorry. That's fine. You know, do what you need to do. Yeah, this works pretty well, actually.
Yeah, it dries quick.
Yep. Okay. I guess I'll start here. Okay. Hi.
Hello. So I didn't understand how you got this condition.
Oh, so what I did is I said if f gets too small, this number gets bigger than L. So I don't have any more arc length to go, so this solution must obtain only when f is sufficiently large. And how big do you need to be? Well, I need an equality here, so I just solve for f. I set this equal to that and solve, you should get this. And then if it's larger, you're okay. And if it's smaller, then there's no solution of this form. Well, I have to get started here, but I'd be more than happy to talk to you later. Okay. Well, that worked. So, I wanted to give you one final thought on this. Yesterday, I was talking with some people later, and they said, well, so the point of your first lecture is that you can sort of package all the elastic details of what's going on inside the cross-section of your rod into a number or perhaps two numbers. And then everything else now you can think about as, being a description of the space curve, really. And that was the point. But then this is, well, when does that break? Actually, this experiment gave you an example of where local details that you thought you had packed away come back to haunt you. The reason is that if you think about what's actually first being built, is that the inner piece of DNA, the way I drew it, actually has a break in it because it was two single-stranded pieces like this. The outer strand is one continuous single-stranded piece of DNA. This is what they call a nick. There are enzymes which will go fix the nick for you. The problem with having the nick, though, is that if you put enough torque on this, which you're doing here, you end up actually locally melting the DNA or breaking up the base pairing interaction and creating a hinge. So it turns out that if you make a short enough piece of DNA here with a nick, you think, oh, I'm really going to pull really hard on my protein. And the answer is you don't pull on it very hard at all. And it's essentially the same idea as taking a drinking straw and bending it, bending and bending it until all of a sudden the curvature collapses into this one little defect, one little kink in the drinking straw. And you can eliminate that by putting in an enzyme which goes and actually, whose entire job in life is to go and repair such things, so it does so. That's the beauty of biology. There's a nano machine already designed to do what you want half the time. But this is actually an example where if you want to study this problem of torque-induced DNA melting, you actually have to build a model with extra internal degrees of freedom. At very least, you need to have sort of an internal Ising variable which says melted, not melted. And the way that that interacts with the space curve representing the double-stranded DNA is that the local bending modulus, the EI, is very weak or very small where you have melted, and it's very strong where you don't. So in fact, you can melt the system even though that's thermodynamically not favorable when you leave it alone, but the system can actually find a more energetically favorable state by locally melting and then collapsing all this elastic deformation into a soft region. And in fact, that's something that we worked out in the past. So, yes, much shorter. Right, exactly. So now we'll move on to new things. Since I think, I forget who, and I spoke about this in the afternoon yesterday, I thought I'd just mention that this is my favorite example of where small internal degrees of freedom come back to haunt you. So we're going to change topics a little bit and ask at finite temperatures, or equivalently at long, or at sufficiently high temperatures, or equivalently sufficiently long bits of filament, you would expect to see all kinds of wiggles. And in fact, what we have is we have an equilibrium ensemble of shapes. What I'd like to do is convince you that we can characterize that ensemble now. I'm going to do so in the following way. I'm going to introduce an idea called persistence length, and I'm going to derive for you the relationship between this new length scale in the problem and the bending energy that we already talked about in temperature. After all, that's all we have to work with. So it better come out of that. And really, you can think of this as a problem of diffusion on a sphere, meaning this is the diffusion of the tangent vector. To set up the problem, I want to introduce a new quantity. This is going to be the probability, which we'll have to figure out how to calculate in a minute, but first let me define what I want to get. I would like to know if the filament is, I'm going to not worry about torsion. If the filament has a tangent vector Ti at one point here, and if I walk along this curve a distance L, what's the probability that I observe Tf at that point here? So this is a conditional probability statement. I'm saying if I know something here, what's the probability I know something there? And you can tell that if the probability decays rapidly to just 1 over 4 pi, meaning it's equally likely to point in any direction, it corresponds to a very floppy object. It corresponds to the fact that here, the fact that I pinned the tangent gives me no information whatsoever over here. On the other hand, if in fact this turns out to be a delta function, if this is the same as that, it means that I have a stiff rod and I know exactly where all these points are for out to that distance. So this is the prob of finding Tf a distance, and by distance I mean arc length, down distance L down the filament from tangent Ti. Okay, so let's see. Here we go. So I know a couple of things to begin with. It had better be true that this function only depend on the difference in the tangent angles, because after all, an overall rotation of the picture shouldn't change anything whatsoever. There's no special directions, in other words. And fortunately, I have a pretty good sense for the energy cost associated with bending the filament locally. Let me write down the following and see if we agree with it. If it, in fact, it better be, right? Yeah. So I think I should write that. Yes, you're right, because after all, what I mean is if I rotate it, if I rotate the whole picture, it looks the same. That's right. I'm sorry? Oh, the cross-section, yeah. I'm going to ignore torsion, and I'm going to assume I have a circular cross-section, just to be as simple as possible at this point. And in the same way that the isotropic version of elasticity is sort of the go-to for most things, this sort of analysis is usually the go-to for most filament-based statistical mechanics. If, in fact, I have a small distance, this problem gets a lot easier. After all, I know that it's very hard. It's a high-energy problem to bend the thing dramatically on a short distance. So I expect the following thing to be true. If epsilon is sufficiently small, I should be able to write this in terms of some sort of normalization. And I'll come back to that in a minute. We can decide what that normalization should be. Here I have the energy cost for bending a little piece of filament. And in principle, I should write this as an integral over all possible paths in the way it goes, but I'm going to use the fact that I'm going to take epsilon to be small in just a minute. So here we know from our energy, this is what we have. Yeah. Should I erase this and start? Or should I? Okay. The stuff inside the integral, sure. Let's go. So, in fact, at this point, I don't even have to say that epsilon is going to be small. What I'm saying here is I'm writing an integral. I'm going to sum over all trajectories of t on the unit circle. It's wiggling around however it chooses to. And I'm going to weight them by a Boltzmann weight, which is the arc length derivative of t, like so, squared. And that's exactly what we had for the elastic energy, assuming circular cross-section, and I don't care about directions. So I have one number out here, which I've already ruined my notation. Kappa is E times I. Yeah. Oh, yeah, but I need I'm sorry. Yeah. I want ds here. Yeah, I want a regular ds here, and I want to integrate over all. Thank you. Oh, there we go. So now, if I'm going to do this, this turns out to be much easier now if I think about going over a short distance. Let me write this in terms of a local difference. So I can write this thing in, now I'm using the small epsilon limit. I can write this as Tf minus Ti quantity squared over epsilon squared. That's my derivative here. And now I had to integrate a little bit of ds from 0 to epsilon. So I get an extra factor of epsilon here. And now the only thing I need to do is I need to guarantee that n is chosen in such a way that in the limit epsilon goes to 0, this has to approach a delta function. So what I'm saying is that I have a very narrowly peaked Gaussian here. And as I take epsilon to 0, I have to get that Gaussian has to shrink down in just the right way to give me a unit area under the curve so that the probability of pointing somewhere is 1. Okay? Good. So, almost forgot my trick. Now you might say, well, it isn't very helpful necessarily to know what happens epsilon away. What I'm going to do, though, is I'm going to derive from this statement a differential equation for how G evolves with arc length. So to get there, I can think about the composition of probability. What I mean is that if I want to know the conditional probability of observing T final at not L, but L plus a little bit, I can think of this as the probability of observing T final, or going forward from some other T to T final over a little piece of distance, times the probability of starting out at T initial and going forward to this new unknown intermediate T, and then I have to integrate over all possible T intermediates. And of course, this is an integral over the unit sphere. So you can think about this as the following picture. Over here, I start off going T initial. Over here, I'm at T double prime. And looking at the equation now, I have absolutely no idea what happened to T prime. There isn't one, so I just copied my notes. It just seems unnecessarily primey. And here I have T final here. So it's a little bit like saying the probability that you got from Denver to Boulder can be thought of as the probability of getting from Denver to somewhere else times the probability of getting from somewhere else to Boulder, and then integrated over all intermediate places you could have gone. Except now we're doing it for tangent vectors. Okay? The advantage of this is that we have a small parameter here. In fact, they are correlated, and the correlations are built directly into this function. This function is telling me the correlations in the tangent vectors. And I want to derive what that answer is for you. Okay? So give me 2 more lines, and I think you'll see how it's going to happen. What I want to do is I want to say, even if I don't know what G looks like a priori, I can tell you how the derivative of G with respect to arc length is going. Okay? You might have seen something almost the same thing before in terms of deriving the Schrodinger equation from a path integral approach. So, the amplitude to go from dot to dot is the amplitude to go from dot to some intermediate spot to the final spot integrated over the intermediate ones. It's the same sort of thinking. So, what I'm going to do, the only thing that makes this a little bit tricky is that we have to be careful to remember that all of these transitions from one spot to another are just rotations. So we have to think about that a little bit. I don't think it was that Tom was so strong. It's just that some of this chalk is unnecessarily crumbly. I don't know. That's a bad piece. Let's try again. So I'm going to say that the intermediate spot, the intermediate tangent is equal to the final tangent plus a little bit. And that little bit, where eta is some infinitesimal rotation of the final one here. And the idea is that the size, the magnitude of this little rotation vector has to go to 0 as epsilon goes to 0. And the plan is to stick this in and expand everything uniformly order by order in epsilon and hopefully be able to sort the terms out. The left-hand side of this expression is simple. Yeah, that is the left-hand side. Good. I wrote in my notes the right-hand side where it's obviously on the left-hand side, and it gave me pause. Gesundheit. So, And I won't need those. So what I'm saying is that expanding this in epsilon, I have the epsilon to the 0 term, and I have the first order epsilon term. The thing which is a little bit trickier is the left-hand side. No. Stage left? Good Lord. Okay. Okay. Right-hand side. This is my right hand. Okay. Okay. So. So what I'm going to do is I'm going to expand the last little piece here. And I need an eraser, it looks like. T, I think I screwed this up here, so I'm going to fix it here, I hope. T, like so. Epsilon. Well, the epsilon to the 0 piece is going to, in fact, be a delta function. It's required to be. So what I should do is actually write the whole integrand out for you. That's probably better. One of those. T initial. So expanding this out, the first term is that. Now, I'm going to write down the T initial L T is equal to T final. So we have to be a little bit careful here. I'm standing in front of what I'm writing to. So what I'm doing is I'm expanding this piece out order by order in the epsilons, and this is a first order in epsilon term. This is the alpha-th component of this vector contracted with d by dt alpha. So it's the alpha, I'm taking a derivative with respect to the alpha-th component of the tangent vector, and then when I'm done, I'm setting it equal to t final. And I can keep going. In fact, I need to, because I will not find anything at that order. And I get two derivatives, t alpha, t beta of g. And in principle, I have higher order terms, but I don't need them, because this is my epsilon squared term like so. Now, I think I'm out of time, and it's really an inconvenient place to be out of time, but that's the way it goes, I think. It looks like I have 2 minutes. Do you want me to try to finish this? Or do you want to finish? Okay. I probably need 5 minutes is the problem, so that's where it's, okay. Okay. Well, you said it with such enthusiasm, too. So I really feel like I am now obligated. So now remember, I also have this exponential piece that I need to look at. This is exponential kappa 2te. Remember, after all, this difference is just the small rotation. So, and now I can, in fact, work out what this is. What I really mean here is the dot product of this with itself. And if you work that out, you end up with here minus something which doesn't do me any good because it points along the rotation direction. I'm not looking at the torsion piece. So Notice that this is now if I want to integrate over all of these small things, which is the point here is I had to integrate over all these intermediate ones, which means integrating over all of these small angles. And here I have a quadratic. So that's nice. It means that anything linear in delta theta is useless to me, goes away. And the quadratic term actually forces alpha and beta to be equal to each other. Otherwise, I don't get anything. So in other words, I'll skip one step. It ends up that what you really need to do is compute the following. I feel like we have seen plenty of indices today, but so we'll see only two more. T alpha, T beta. So what I mean here, what I mean by the braces is I'm doing the Gaussian integral over this. And what that did is it actually forces alpha equal to beta here. And these antisymmetric tensors are born from the cross products that are up there. And you can sort that thing out. The nice thing is that at the end of the day, in fact, you don't have to go any farther, this is just the average of this piece times this squared. So if you think about it, this is nothing more than the generator of an infinitesimal rotation of your tangent vector, and it's squared. You might say, oh, I have bad things happening because I have lots of epsilons floating around, but I also have a 1 over epsilon here, and that knocks my epsilon squared down to epsilon. So now I actually have a fair fight between the left-hand side and the right-hand side. So collecting terms. Yes, exactly. I'm going to say that that's a very good point. So what I'm going to do here is I'm now going to extend this integral. And I'm doing this so, in fact, this is a vector that has two components because I don't care about the piece along t. And when you do that, you'll collect terms and you arrive at the following. D by ds of this probability distribution with respect to s is in fact equal to t over 2 g itself. So this is basically a diffusion equation. The only thing that makes it a little bit more complicated is you have to diffuse around on a sphere. You don't get to diffuse around in the Cartesian world. But otherwise, nothing as horrible has happened. And this is the diffusion constant. If you want to try it yourself, I recommend that you do. And in fact, if you want to make it more interesting, you can try to ask yourself what happens if you do this not in 3 dimensions, but in d dimensions. And if you do that, you will find a factor of d minus 1 over 2 coming in. Notice when you take d equals 3, this becomes simple. So it drops out. But anyway, you can try this yourself. So in the final lecture, which I thought would have been today, we will end up with the diffusion, we'll end up with the persistence length, and we will talk about networks and pulling on filaments and such things that are now at finite temperature. I am sorry to go over. I apologize for keeping you, and thank you for your time. Oh, God. Let's see.